Push that rock here with Simpson math. Integration by trig substitution. Let's try to integrate this integrand right here. First, let's look at the radicand. So the radicand is x squared plus 2x minus 3. Let's look at that and let's do some. Last time I taught this, I think I was really stupid compared to some of y'all. I saw some of y'all doing this, just rewriting this -3 in such a way that you could get a perfect square trinomial. That was so genius. So I'm going to mimic you guys and learn from my students. So I just rewrote the -3 as 1 minus 4. And that gives me a perfect square trinomial. See, this factor to x plus 1 times itself. So I have x plus 1 squared minus 4. And I can see that if I let u be x plus 1, so that du is just dx. And if I were to need it, then u minus 1 would be x if I were to need it. But what the main thing is, I can put this u in right here, and I have a u squared minus 4. Now, if this was 4 minus u squared and it was under a radical down in the denominator, I'd be thinking arc sine, right? So if we're integrating 1 over the square root of 4 minus u squared du, then you get arc sine. I don't know if y'all can see this. But anyway, but that's not what we have. We have u squared minus 4. So that's okay. We have this trig sub secret. If you see anywhere, it doesn't even have to be under a radical really, but if you see variable squared minus constant squared, then there's this nice little trick that leads to a great substitution where you substitute a trigonometric relationship for your algebraic one in order to make the integration easier. And the trick is to take the variable and set it equal to the constant times secant of theta. Okay, so that's the little trick. So in our case, we have the variable is u, and the constant squared is 4. The constant squared is c squared. C for constant is 4, so c is 2. So I'm going to say 2 sec theta. Okay, now to do that, we need to see a triangle. Okay, so set this little secret aside. And here's my triangle. And remember, we are letting u equal 2 sec theta. Now, sec is a reciprocal of cosine. So cosine is adjacent over hypotenuse. So secant is hypotenuse over adjacent. Well, I'm going to divide by 2, and I get u over 2 equals sec of theta. So this is the hypotenuse in my triangle. It's very important to label your theta because you need to know what's adjacent, what's opposite. The adjacent is 2. Now I'm going to complete the triangle. I want to label all the legs. So I have the hypotenuse labeled and one of the legs labeled. So I'm going to complete it, and that means we go one leg squared plus the other leg squared. The other leg is 2 is equal to the hypotenuse squared. So I have a leg squared is equal to 4 is equal to u squared, because u is the hypotenuse, and so the leg squared is equal to u squared minus 4, and of course then the leg is equal to the square root of that relationship. So this leg is the square root of u squared minus 4, because we take the square root there. Okay, so now I have my nice little triangle. That's nice. Now I'm going to be doing some trig sub. I'm going to substitute in this something with theta in it. So that means I'm going to need to get rid of u, so I need du. So let's get du. Looking up here, looking at this, I'm going to get the derivative, the differential of u. So I get the derivative of this d theta. Well, the derivative of 2 sec is 2 sec tangent, because the derivative of secant theta is secant theta tangent theta, and then don't forget your d theta. And then I'm going to look at my triangle and look back at my original integrand and find something that's useful. So we need to get back to that original integrand for a minute. So let's go back to it. So we're going to look here and we're going to see that, hey, This x, remember, was u minus 1. Remember, we said that somewhere. It said that if we let u be x plus 1, we might need u minus 1 to be x. So that x is u minus 1. And then we did some work to make this u squared minus 4 du, where u is equal to x plus 1. So if I plug in x plus 1 for all my u's, I can get back to this. And then, of course, I'd have dx. So that gives me this. Now I'm going to bust this up into two integrals. I have u over the square root of u squared minus 4 du. And you can definitely do a double u substitution now. You know, if you let, for that part, we still have another part over here, but for this part, we can let w equal u squared minus 4. So dw is 2u du. And then we can put a 1/2 here and a 2 here so that we can do the substitution. I'm not going to bother with that. You now are experts with u substitution. I'm going to focus on the other side. We have 1 over the square root of u squared minus 4 du. And here's where we're going to go back to our triangle. So we see that we have this. We look at our triangle, and there's no relationship with 1 over, but there is a relationship with 2 over this, and that's easy to get. So I can make this a 1/2 and change this to a 2. So 1/2 of 2 is 1. And then I realize, looking at my triangle, that 2 over this is cotan. So cotan of theta is the adjacent over the opposite. So there we go. I can plug in cotan of theta for this. So I have minus the integration of cotan of theta. Now I have to, this is the most common mistake, is not replacing the du. I can't have, if I have a theta here, this has to be d theta, not du. But remember, we have that. We have that du is the same thing as 2 sec theta tan theta d theta. So I get a 2 sec theta. Oh, I forgot this 1/2. That's going to be important because 1/2 of 2 is just going to go away. Tan theta d theta. I hope y'all can see that. I'm kind of squeezing it in the screen there. Now, look, cotangent times tangent, they're reciprocals. These are reciprocals. Cotangent times tangent are reciprocals. And 1/2 times 2 is 1. So we have just the integration of sec theta d theta. And we know how to handle that. You just go bananas. So go bananas here. Did I spell bananas right? Go bananas. Multiply by just a freaky, crazy circus trick 1. You know? I don't know if y'all remember this, but we did it in class. You can multiply by sec theta plus tan theta over itself. Tan theta plus sec theta. Change the order down here. Because now when I distribute the sec, I get secant squared. Oh, guess what the derivative of tangent is? It's secant squared. And then I get secant times the tan. Guess what the derivative of secant is? It's secant tan. So if we let, I don't want to use u because we've used u already. So, and we've already used w, so we'll use v. Okay. V, if we let v be the denominator, tan theta plus sec theta, then dv is exactly the numerator, secant squared, because the derivative of tangent is secant squared. The derivative of secant is secant theta tangent theta, and then don't forget your d theta. So, and notice that's what we have. We have secant squared, and then we have secant times tan, so secant times tan, d theta. So we can just put in v for the denominator, the integration of 1 over v, and then in the numerator we put 1 dv. So that's why I put the 1 there. It's 1 dv. And then in the denominator it's v. And then we know that's the natural log of the absolute value of v. But what was v? Well, it was secant plus tangent. Now we're not done. So we'll do this on the next sheet of paper. And I'm still leaving, this is still out here. So, you know, it's still out here. So to finish this problem off, then we're going to remember that we have this 1/2 the integration of 2u over the square root of u squared minus 4 du that you're going to finish with w substitution, minus the natural log of the absolute value of v, but v was tan of theta plus secant theta. Now, but what was theta? Remember, we need to deal with this. Tan of theta, go back to your triangle. Tan of theta is the reciprocal cotangent. So if cotangent is this, then tangent would be this over this. So the opposite over adjacent. So we have the square root of u squared minus 4 over 2. Plus secant theta. What's secant theta? Well, secant theta, remember, we already have that. It's u over 2. And then don't forget your plus c. Now, this combined with whatever the antiderivative this turns out to be, and maybe I should do it, but I don't think it's worth the time of the video, but is going to be the answer. However, if you start Googling this and saying, oh, I want to check it, well, you know what? To check it, you should just take the derivative of your answer and see if it works. That's what you should be doing. But I know some of you are Googling it, and you're not going to see these 2's down here if you do. So let me show you why they vanish, okay? Why do they vanish? Well, we have the natural log of this can be added up. So it's the square root of u squared minus 4 plus u all over 2. And now we have this, I don't know why I'm keeping the plus c, we're just focusing on this. Now we have this log property that says that the natural log of the numerator, that should be a minus 4. I don't know why I'm getting sloppy here. This video is too long, I'm bound to make a mistake. Plus u minus the natural log of 2. Okay? Now, this is an absolute value bar here. Okay, good. Now this negative goes to this, and and you get the absolute u squared minus 4 plus u. And then this negative applies that, and I have a plus natural log of 2. But the natural log of 2 is just a number. It's approximately 7/10. If you type it in the calculator, it's going to give you 0.6903, blah, 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 blah. Okay? So it's just a number. And when I add that number to c, I just get c. It's just a constant. You see that this function is simply a vertical translation of this function. See, it's been shifted down natural log of 2 units. So anytime you have two functions that are vertical translations of one another, they're both antiderivatives. So the books and all the online websites will write the answer this way, making this 2 vanish. Don't forget, you should finish. There's some function here that I didn't bother to get because it's W substitution, and you're good at substitution. Math made simple. It's Simpson math.